Before we jump into this short modular arithmetic proof involving factorial, remember a way to define factorial. This is, I guess, not particularly common, at least not from what I've seen. But if we have I equals 1, let's say, or well, not let's say, that's it, to n of I, this literally means to put a 1 there, a 2 there, a 3 there, all the way up to n, and then multiply them together. Well, guess what? That's the definition of n factorial. Okay, now again, I've seen this in Van den Einden's number theory textbooks, but I don't see it that much. Maybe this is a definition of n factorial, but usually they write it the other way, just 1, 2, 3, 4, 5, 6, all the way out to n explicitly. But this is a way to write it more compactly with the pi product notation. Now, what we want to show today is that the product of the first n cubes is congruent to n factorial modulo 6. And it's really fairly straightforward. If we can establish that this is true, we'll be done based on just putting this together with this, right? So one way to prove this, folks, is just to do it modulo 2, and it's trivial for modulo 2, 0 and 1 trivially work. And then do modulo 3, and then you'll see that 0, 1, and 2 work, okay? Another way to do it algebraically is just to consider I cubed minus I. Okay, because this is the same thing as saying, does 6 divide I cubed minus I? Same thing. This means the same thing as this. Now notice this is equal to what? I times I squared minus 1. Now you'll recognize this as the difference of two squares. And so allowing for the rearrangement here, I'm going to write this as I minus 1 times I plus 1. And we see we have the product of 3 consecutive integers. Okay. Now one just prominent fact of 3 consecutive integers is exactly one of them is a multiple of 3. And of course, we have consecutive, we have even integers all over the place here, right? Or by parity, there would be at least one even integer in here, if not 2. But this would be equal to the 3 that I just mentioned, right? Again, 3 consecutive integers, for example, 7, 8, 9. 9's a multiple of 3, right? And there's going to always be exactly one multiple of 3 in the product of 3 consecutive integers. And also, of course, 2's in there, evidently. All right, and so we'll put times 2, and then we'll just put the customary m here. So you see, that proves this, okay? That statement proves this because, again, I cubed minus I is equal to a multiple of 6m is another way of stating that, right? So that's the proof of that. Now, let's move along. Now you see it just follows immediately because all you got to do is just replace. See what we did here? We showed that I cubed is congruent to I, so we replaced I cubed with I, which is legitimate in congruence arithmetic. And then you also see that we showed earlier that this is just an alternate definition, right? This right-hand side down here is just an alternate definition of n factorial. So without rewriting too much down here, we have n factorial. Or is this part right here is just equal to n factorial by definition. Okay, so we can write QED at this point. Now it's kind of fun to see a concrete example. The numbers grow pretty fast right here, but notice, let's just try for n equals 3. If we did this for n equals 3, that would be the product of 1 cubed times the product of 2 cubed times the product of 3 cubed. And y'all, this is 8 times 27, so that's equal to 216. It's equal to 216, right? Now, notice that 3 factorial is equal to 6, right? So this is equivalent to looking at 216 minus 6. equals to 10. Right, let's see, that better be a multiple of 6. Yes, it's 6 times 35. Okay, so you can see that it works right here. Again, we just used n equals 3. We got the left-hand side is equal to 216. The right-hand side is equal to 6. 216 minus 6 is a multiple of 6. So this is a concrete example that it works, and it works out. You can check it out, but it definitely works. So we did find another way to represent in factorial modulo 6 for whatever that's worth. It's be maybe a problem somewhere. If you use that fact, it might be part of some other problem not at an Olympiad level, perhaps, because you'd have to, usually the trick is to have one sort of obscure result that you have to rely on to make it an IMO problem, or not IMO, but some kind of Olympiad problem, right? Okay, that does it, folks. Go solar system.